All right, you crazy kids, here's your lecture on stoichiometry. Now, stoichiometry looks like a big scary word, but it shouldn't be, because in chemistry we use stoic all the time. Calculations of quantities of substances involved in chemical reactions. Here we see a chemical reaction. This should look pretty familiar to you at this point in time. It's the decomposition of aluminum oxide with heat to produce some aluminum and oxygen. Now, previously we talked about these coefficients and their need because you have to have the same number of things on each side of the reaction. I never really told you a number of what things. In reality, the reaction literally reads 2 moles of aluminum oxide decomposed to produce 4 moles of aluminum and 3 moles of oxygen gas. So these values here are actually molar amounts. All right, in chemistry, that's what they stand for. So we're going to use those to start doing some calculations and convert one component into a new component. That might sound scary, but it's really not. Let's take a look at what a question might look like. So, if 4 moles of aluminum oxide decompose, how many moles of oxygen are produced? Now, originally, right here, we see that I'm starting with 2 moles, and I'm producing 3 moles of oxygen. Well, if I double it, if I have 4 moles of aluminum oxide decompose, how much oxygen should be produced? And everyone should probably say, like, oh, it'll just double. So we get 6 moles of oxygen, right? That's great, but generally speaking, I love work. So we have to prove that by using stoichiometry. And it's dimensional analysis. We're going to set this up the same way we've been setting up calculations all year long. So we're going to go with 4 moles of aluminum oxide. Oh, wow, I have a hard time reading threes. Decompose. And we're curious as to how many moles of oxygen are produced. Now, we should see that this first unit here, that's the unit I'm trying to, erase or convert. That's going to go on bottom. So I'm going to have moles of aluminum oxide on bottom. This unit up top is going to be, the thing I'm trying to turn it into, moles of oxygen. So that's the unit I'm converting to, moles of O2. And if we look at it, we can hopefully see that in terms of unit cancellation, this is very similar to everything I've been teaching you all year long. Kind of a method to my madness. So this unit of moles of Al2O3 is going to convert into moles of oxygen, and that's the unit that we're looking for at the end of the day. The conversion between moles of aluminum oxide and moles of oxygen comes from your balanced chemical reaction. So this amount right here is literally coming from the chemical equation that we've just created. The amount up top here is coming from this part of the chemical equation. So I'm going to put a 3 here and a 2 here because that's the ratio of those two components of their reaction. It's a 3-to-2 ratio. Let's see what happens. Now, in terms of a calculation, we have 4 moles times 3 moles divided by 2 moles. All right, so 4 divided by 2 times 3, dun dun dun, we get the same answer, 6 moles of O2. Okay, so we got the same thing we got up here just by using our brains because we just doubled it, but now we're proving it with calculation. You can do this with any component part of the reaction, all right? If I were to quickly ask you, like, okay, if 13.6 moles of aluminum are produced, how many moles of oxygen are produced with it? So once again, now I'm looking for moles of oxygen. I started with moles of aluminum. Okay, well, moles of aluminum is going to go on bottom, moles of oxygen is going to go up on top, and the values for the ratio that convert one of those things to the other thing, which is stoichiometry in general, come once again from my chemical equation. So here's my aluminum, that's going to go here, 4, and here is my oxygen, that's going to go here, 3. Oh, my 3s are so bad, 3. Now in our calculator, this literally reads, right, 13.6 times 3 divided by 4. So that's all you have to do to get that answer. 13.6 times 3 divided by 4. And we get 10.2. In terms of sig figs, in this case, I start with 3 sig figs. That means my answer is also going to have 3 sig figs. The ratio, part of stoichiometry, the whole point of stoichiometry, converting moles of one thing into moles of a different thing, does not take in fact with significant figures. We're going to call these, infinite number of significance, these whole numbers that actually bounce the equation. All right, now, we have one more practice problem here. Get you guys rolling. If I needed, you should probably pause right now and try this one on your own. If I needed 3.27 moles of oxygen, how many moles of aluminum oxide would need to react? Okay, so now I'm starting with 3.27 moles of oxygen, and it's asking about moles of aluminum oxide. All right, well, what do? All right, well, moles of oxygen goes on bottom, moles of aluminum oxide goes up on top. Notice how I'm filling in my units before my values, and then I look to my problem up top here. Here's my aluminum oxide, that's a 2, and here's my oxygen, that's a 3. So, once again, I plug it into my calculator, 3.27 times 2 divided by 3. I get 2.18. Let's move this over a little bit. Moles of aluminum oxide. I start with 3 sig figs, I end with 3 sig figs, everything's cool. Now, that is stoichiometry, okay? So it's converting moles of one thing into moles of another thing. If we look at it, I'm going to delete some of this messiness just to kind of clean it up a little bit here. That looks pretty good. Every single time, what I'm really doing is stoichiometry right here, right? This is the heart of stoichiometry. It's moles to moles. Moles of one thing into moles of a different thing. Right? We gave 3 examples on there. That's all stoichiometry is. However, just because chemistry always deals with moles, but in our lab, we don't really have a balance that reads out in moles, we're probably going to have to do some conversions. So when I told you guys converting grams to moles is something that's going to become second nature to you, I was not lying. In this case, we're going to have to do some conversions. I have a question here. 3.34 grams of aluminum oxide react. How many grams of oxygen are produced? So it looks like I'm starting with grams and I'm ending with grams. Stoichiometry, I've made this quite clear, is moles to moles. I cannot use, this balanced equation up here in terms of grams. That's only molar amounts, all right? Here it is again, proof to you. Moles, 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 right? So it's only molar amounts. So if you're dealing with something besides moles, you're probably going to have to convert to moles. And that's all stoichiometry really is. So it looks like we're starting with grams, we're ending with grams. That means I'm going to have to do another couple conversions here. The very first thing I'm going to have to do is take my 3.34 grams of aluminum oxide and convert it from grams of aluminum oxide to moles of aluminum oxide. Now that I have moles of aluminum oxide, I can use stoichiometry and convert my moles of aluminum oxide, 3s are so hard for me, into moles of oxygen. All right? And then once I have my moles of oxygen, since the problem is asking for grams of oxygen, I can do another conversion here. And I'll move my moles of oxygen into grams of oxygen. That is the whole problem, all right? These are conversions between units. In this case right here, I'm converting grams to moles. In this case right here, I'm converting moles to grams. Both of those values come from the periodic table. I've shown the work over here on how to actually do that. All right, the very first one, my grams to moles conversion with aluminum oxide, we have 1 mole of aluminum oxide is 101.98 grams of aluminum oxide. No big deal. Over here, I have moles to grams of oxygen. All right, well, I've already done the work for you. 1 mole of oxygen is 32.00 grams of oxygen. Oxygen is a diatomic, so I had to multiply it times 2. The heart of stoichiometry, right here, comes from our balanced chemical equation. So we're going to go way back up to the top. Here it is. I need to know my moles of oxygen ratio to my moles of aluminum oxide ratio. So for every 3 moles of oxygen, I have 2 moles of aluminum oxide. I did this a very specific way for you guys, okay? I used all my units first, and then I started filling in all the numeric values. You gotta work your units before you start doing anything else. If your units don't cancel out, you'll never get the right answer. Please work units. Chemistry is all about units. I've been very clear about that. If we take a look at our unit cancellation, we'll do it in red. We have grams of aluminum oxide converting into moles of aluminum oxide. moles of aluminum oxide converting into moles of oxygen converting into grams of oxygen, and grams of oxygen is what we actually wanted. That's what the question is asking for. So work your units and then worry about the values. Plugging this into my calculator is pretty simple. I can ignore the ones because when you divide by 1 or multiply by 1, it's the same value you start with. So in my calculator, I'm doing 3.34 divided by 101.98 times 3 divided by 2 times 32. And that gives me this fun answer of 1.57207. Okay, well, that's not going to be great because I have way too many sig figs there. But I start with 3. That means I'm going to end with 3. So this is going to turn into 1.57 grams of oxygen. In terms of point values, because I know you guys love to figure out how I'm going to grade this, you're going to get a point for your first conversion from grams to moles, a point for the stoichiometry, which is a mole to mole conversion, a point for your mole to gram conversion, a point for your answer, a point for sig figs, a point for your unit. You're also going to get a point for adding up the molar mass of aluminum oxide and a point for adding up the molar mass of oxygen. This one right here always gets kids. They don't want to do it. They say, oh, I just double it. You have to show your work. In reality, this is a pretty big problem. We have 1, 2, 3, 4, 5, 6, 7, 8. Really? 8 points. Wow, that's the worst looking 8 I've ever seen. Let's try that again. 8 points. Good golly. That's a lot. Is it actually 8? Let me count again. I feel like a crazy person. 1, 2, 3, 4, 5, 6, 7, 8. Wow, 8 points. But it's a lot of work. And that's stoichiometry. Hey-o.